Okay, by chance, Manuela Professor Veloso is the Herbert Simon Professor at the Carnegie Mellon, so we have quoted many times Simon for the bounded rationality principle and the famous ant on the beach. She is actually, I think, no, is still president of a AAAI. And actually, I think that she recently, among the many things that she did, recently she introduced the concept of symbiotic autonomy, that I think it's kind of Columbus' egg about how to complement the intelligence. We know that robots and artificial intelligence are still very limited. So the idea, if she will talk about this, but the idea that, well, if they understand they cannot push the button of a lift, maybe they can just ask you to push the button. This seems almost trivial, but I think it's extremely deep. And it also could bridge the long way that we still have to have real artificial intelligence. But I don't want to steal the time. I thank you for being here, and I'm ready to listen to your talk. So the floor is yours.
Should I start?
Yes, thanks.
Okay, great. So I'm going to tell you a little bit about the concept of autonomous robots. And like Fabio introduced, I'm going to explain how they ask for help. But my talk is about the complete autonomous service robots concept. And I have to thank my students Joydeep Biswas, Brian Colton, and Stephanie Rosenthal, who actually finished her PhD recently, and Brian is finishing also this year. Okay, so this research I'm going to tell you about on this problem of autonomous robots has to do with this quest that for making like creatures that are intelligent and can process the main capabilities of humans integrated, namely, we are robots that are capable of perceiving the world, making decisions about the world, and eventually acting. So this integration of perception, cognition, and action is indeed what makes them be autonomous and puts together artificial intelligence and robotics as areas. So I'll try to explain these service robots that can ask for help within this context. So the next thing I'm going to tell you is that some time ago, I put myself this question about whether we can have, in fact, these robots coexisting and interacting with humans in our environments. And many experiments have been done, and a lot of research has been done on this problem. But I really wanted to see how does it take to make them be there within humans. So the first thing we did was that I built these robots that you can see on this picture, which are basically a mobile platform, so a very beautiful omnidirectional mobile platform. And the robots were designed and built by Michael Lasitra. And they have a sensing and reasoning or computing device, which is a laptop and a Kinect or other types of cameras, but in our case is the Kinect. And the most important aspect for me was, at the beginning, was to really assign them tasks, so that these robots would not be in the environment simply to map the environment, but to actually do tasks for humans. And so we introduced these multiple tasks. We started actually with a visitor companion, and then we did semi-autonomous telepresence. But then now the robots are autonomously going to locations, delivering message from one place to another, escorting visitors, transporting objects between locations. And all of these was very important for this concept of actually getting them to perform tasks. So in the next slide, I'll show a video of an example of the go-to-location task. And in this, so maybe you can take the sound off. We don't need the sound. Well, thank you. And so this robot moves in the environment, and that's what I'll explain how it does. But the interesting thing is that it's completely autonomous, goes everywhere in the building. Our building has 9 floors, and it has 350 offices. It goes in the building and is capable of stopping at the right location, at the destination location. So what is going on here is what I'll try to explain now next. And but what I want you to observe is the fact that indeed it navigates and has a destination, and it stops there. So let me just explain the outline of my talk. So it will have 3 parts. I'll very briefly explain the task scheduling. Then I'll spend some time on the localization and navigation, and then I'll finally introduce the symbiotic autonomy. The task scheduling part is rather important to us because it enables users in the building, people that want to use the robot for services, to request tasks. So we developed a web interface, also an on-board interface on the robot if someone needs the robot, which I'm not illustrating here. But the outcome is indeed that the users can request particular tasks. And then the tasks themselves are passed to a centralized server. So they are either remotely passed wirelessly to a centralized server. And also we have a scheduler on board of the robot. But for the purpose of this talk, it's okay to think that there is a centralized server which forms schedules for these tasks requested by the users. And interestingly, for multiple robots, according to predefined objectives such as minimize time and scheduling constraints that may be present. So this cycle is, in some sense, the service cycle of the robot. Gets tasks, someone schedules exactly where to go for multiple of them, and the robots then eventually execute the tasks in a with some symbiotic autonomy, as I'll explain. So the next slide, I just give a simple example of what it's missing a picture. I don't know, in the PDF a picture is gone. But it's just giving an example of a schedule, and you can see here that the schedule gets all these tasks and then it assigns autonomously whether it should go to CoBot 1 or to CoBot 2. Okay? So the outcome of this process is indeed destinations that the robot needs to visit. So this task scheduling part includes a lot of AI research in terms of trying to represent tasks with specific all the features of a task that are needed, and then in fact schedule these in a novel where we introduced also novel ways to schedule them so that they can share resources among them, and that's Brian Colton's PhD thesis, which you can look at the end. I have the references. So task scheduling. So now you put aside this problem, but you know now that the robots have a destination that comes from requests from the users. And now I'll explain a little bit about the localization and navigation of the robot. In the autonomous localization of a robot is a problem well known in the literature, in the research community, and it consists of the following. It consists of assuming that our algorithms, the robot algorithms, have some prior probabilistic models of sensing, meaning like what is the probability of observing, sensing specific features of the environment given some map location. So if you would know where you are in a map, what should the robot see? So this sensing model is given. Then you have a motion model which allows the location to be updated given the actual motion of the robot. This is also given because the robot, it's on motors. You know that if you send to the robot a particular motor velocity, that the robot will move by this much. And of course, these prior models are probabilistic because there is some variance in the actual execution of the robot. So the algorithm starts with these models, and then is given an history of observations and of robot actions. And basically, the localization problem is to estimate at runtime, when the robot is executing, what's its pose. So basically, what is its XY location and orientation data in a map. This is a map of the building, and this particular one is just a map that we got from a PDF file that has the long-term features, the static features of the environment, the walls. All the other dynamic features of the environment or slightly changing features of the environment, like tables and chairs and people, are handled in the navigation part. So the localization uses the static features of the environment and some of the short-term features of the environment, the dynamic, but that's a different algorithm. That's a non-Markovian localization algorithm, which is the thesis of my student Joydeep Biswas. But let me just tell you that this pose belief estimation becomes the result of 4 steps. You predict from the motion model and the real action where your belief of where the robot is should be. Then you update this belief based on the sensing model and the actual observations to reinforce belief, given that you start with a distribution, with a random distribution, or that you want to reinforce your belief. You resample your distribution according to the current value of the estimation. And then we introduced also this step that constrains the distribution based on map properties, such that estimates that are outside of the real corridors of the building are erased. So this is like an example of the first step, which is the sensing step based on depth, in which the left image shows the view of the robot as a depth 3D point cloud. And for the robot to actually navigate, we had to develop algorithms that are very sophisticated in terms of real-time processing. And we have done these through introducing this fast sampling plane filtering algorithm that allows planes in the image to be identified such that the robot can identify the walls of the building. So the next video, if I can have the next video. In this video, you can see that the robot is in the map has an uncertainty level, which are the red circles you can see. And when it's in open areas where it did not sense, and when it actually senses the wall and tries matching it to the map, its uncertainty decreases and the robot moves. And you can see on the right the image, the raw image, and then the process image with the plane filtering algorithm that can actually ignore the outliers that are not planes, such as a person moving in the environment, and well maps the planes to the actual map. So with this, can I see the next video with the robot moving? With this autonomous localization and navigation, the robot actually traverses a wide variety of different environments. In this video, you can see like an area of a corridor where the floor is the wooden floor, then it enters another area where it's an elevator, and it's like much brighter. It goes through a bridge that's very bright, and then between the bridge and the carpet again, there is a little bump, and the robot in the map has the bump annotated, and it's capable through localization to find out that it's exactly in that position and really slow down there to make sure that the hardware on board of the robot remains safe. So that is this is a video of a common performance of the robot in this challenging environment. Okay, so in my outline, I told you about the task scheduling. I have limited time to tell you about things in more detail, but now you have the concept of this localization and navigation. So you have the tasks, the robot gets locations where it should go, and then there is an algorithm to actually execute these tasks in the environment through sensing of planes and estimating of pose through prior models and online observations and actions. Then finally, I'll finish by mentioning the last aspect, which is the realization that robots, and in particular these robots, is CoBot robots, but any robot has in fact limitations. So what's happening is that our robot does not have arms, and therefore it cannot pick up objects, but it does have a basket, which is pretty good because it enables it to carry objects. Though it cannot grab them, it still can carry them. But it cannot pick up objects, and definitely when I claim that this robot moves in a building with multiple floors, it does not have an arm to press a button and call an elevator. You could think, okay, the robot could talk wirelessly with the elevator, for sure. It's not the case at Carnegie Mellon at the time. But what matters is that even if it would eventually talk with the elevator, have a small arm to manipulate some objects, or have an arm to manipulate objects, you and I can actually conceive and can understand that even if we would have great actuators, great sensors, that the robot may still always have limitations. There might be an object that's very complicated to be grabbed. That might be a door with a knob that's very hard to open. So even if we add more capabilities to the robot, from my belief, there will always be a bound of the capabilities that the robot can actually have. As humans, I'm not fully capable of everything, and if you ask me to shoot a basket in basketball, I might not be able to do it very well. And maybe if I train more, I would be very able. But a robot, inevitably, even with training, may still have a limit to what it can do. So this was a big realization for us that led us to introduce this concept of symbiotic autonomy, in which we now, from a research point of view, we acknowledge that robots have limitations, but we develop algorithms for the robots proactive and autonomously asking for help. And what this is different from previous approaches or current approaches on sliding autonomy or humans helping robots is that, in fact, there is this help from humans to robots, but it's not started or initiated by the human. It's initiated by the robot in the sense that the robot is the one that finds what it cannot do and proactively asks for help, what it does not know, proactively asks for help, and what it cannot find, proactively asks for help. So it's not that we have anyone following CoBot in the building. We just wait that CoBot asks when it needs help. So in the next, I'm sorry, this slide. So it doesn't, it's not right, but anyway. So in the next slide, you can see that one of the theses of one of my students, Stephanie Rosenthal, was exactly about this planning to ask or to act. So the question became, now the robot either just does it by itself or may have to ask for help if it's too lost, if it's like does not know where to go, or if actually cannot perceive or cannot actuate. So in the next video, there is an example of the robot getting, now here you can put sound, Nathan, please. It does not play? Oh, I see. Oh, okay. Well, this video would have shown you the robot getting to the elevator and asking can you please press the elevator button? And someone would press the elevator button and tell the robot that the elevator is there. And when the robot is told the elevator is there, it actually autonomously plans a route to enter the elevator, enters the elevator, and asks the person, can you press the button, for example, floor 8, such that eventually the person presses the button and the robot gets out when it gets there. So this is an example of an action that the robot needs help for, and eventually the human helps. So as a result, one of the things about this human-centered planning is that indeed, previously, if you look on the left, when a robot used to plan a route to go from some initial location to some final destination, the robot, if our algorithm were optimizing in terms of distance, the robot would select the shortest distance. But now that we are also, the robot also assumes that it may need help for some of its tasks, it actually optimizes both based on distance, an objective that is about minimizing distance, for example, and also a potential human helper. So the robot may generate a slightly longer trajectory if the probability of getting help in the locations of the slightly longer trajectory is higher than the locations of other trajectories. So such new kind of human-centered planning let the robot to perform any actions, but there is always this issue about what if no one helps the robot locally? What if, like, you ask press the button and no human does press the button? So interestingly, the robot sends us email in case it is waiting for help and nobody helps. So, for example, here is an example of an email it sends to our group saying, I have waited for more than 5 minutes for a response to the question, hello, I'm here to take visitor to room 7412, and nobody actually came and answered my question. So it says, can someone please come to this office and answer this question so I can complete my task? So now the robot is alone in the middle of the building, and we know that it's performing its own tasks. If by any chance it has a task that it asked for help and it didn't get the help, then the robot actually just stops its execution and waits that someone comes and helps it. So just as an example, in this graph, I'm showing something that is interesting to observe because of this symbiotic autonomy, which is how is the time that the robot takes to execute a task divided between time that the robot was on its own and time that the robot was being helped or waiting for help. So this graph is just 50 tasks we selected initially. It doesn't matter. They are sorted according to the time that they took. And so the y-axis shows time, and the x-axis shows just just an enumeration of tasks. There is the ordering is just sorted on the time it took. And what's interesting is that the orange part of these bars is the time that the robot was fully autonomous, and the other blues and yellows and dark brown means some other type of like interaction with humans and waiting for help from humans. And so what you want to observe in this graph is that there is not a single task that's all orange. So the robot still needs help from the humans, but there is not a single task also that's all blue, all non-orange. So it doesn't matter exactly the numbers, but this is what symbiotic autonomy is about in terms of execution. Robots autonomously go, autonomously do a great part of the task, but parts of the task need to be filled in by asking for help from humans. And humans can help. So in conclusion, I just want to go over these different aspects of this autonomy, these autonomous robots, which is that in some sense, if they are service robots, we have to find ways to specify task requests from users. And that is part of the task representation, which if I had more time, I would explain to tell you that indeed this task specification is such that it matches the skills of the robot. So we generated this such that it's going to locations, it's transporting things, because that's the actions the robot can do, which are navigation actions. You could have other types of tasks, like cleaning tasks or other types of service robots. But what matters here is that our service robot was this mobile robot in the building that was making these transport tasks. All the tasks are specified in terms of primitive actions that allow us to introduce new tasks complete. For example, delivering mail, or for example, giving tours. So we have done other types of tasks that are all built from the primitive actions as much as possible. So we define tasks as a function of such modules. So that part, if you are interested, there's a lot to learn about that. Then indeed, we have contributed algorithms, or you have to understand that the next step is actually the execution. Because as opposed to just say, go there, you really need to have the robot move concretely from one location to another, and that entails having algorithms to be able to sense the environment, to be able to localize, and to be able to actually navigate safely. It's a whole big area also, and including the safety issue I just mentioned. And again, you can follow that as a topic of itself. Then the last aspect is this proactive handling of limitations. It's very important to understand, what we want to contribute is that this robot, in fact, you can now look at this autonomy of robots such that they don't have to do it all. They will never probably be able to do it all, because not even humans can do it all. Even in specific services, you may not reach a point, even if you are cleaning. You may not know where something is if you are escorting someone. So there is always this issue about the fact that inevitably, when we deploy these robots, they will not be able to do it all. And therefore, we have algorithms, and we now have approaches to asking for help. And the ask for help that I illustrated was from a co-located human, the example of the elevator. But I also showed an example in which it asked for help from remote humans, saying, I sent you email, come and help me. Or what is it? We have done research also on asking for humans for perceptual information. I cannot find the mug in your office. This is the images I have. Please tell me where the mug is. And then we also have done a lot of work on trying to have the robot go to the web and find out if someone tells me, bring me coffee, what is coffee and where coffee can be found. It's another large part of our work. And finally, this help also comes from other robots. As you saw in the first picture, we do not have a single robot. We have actually in the building 3 robots and another robot in a different building, and they all talk with each other. So if a robot is up in the 9th floor, it may tell a robot on the 7th floor that this door is closed, and knowing that the robot on the 7th floor would need to come up, that robot on the 7th floor may reschedule its task. We also rely on multiple robots to optimize their transport and transfer things from one to another. And also this co-location of robots can be used for transfer or remote for sharing of information, which is another type of help. So in summary, you have to, I'm telling you that we are moving one step further in our understanding of autonomous robots, because as opposed to thinking that we enter all the knowledge into the robot and the robot makes inferences and makes decisions, now the robot can have its own knowledge plus accessing and have access to the external world, be it other robots, be it other sensors, be it the web, or be it humans, and complement what it can do with the information and the help that comes from the external sources. All these topics I told you about are available off this website, and the publications support and extend and explain the items that I covered in this talk. Thank you very much.
Thank you. Okay, I guess we may have some question from the global hall.
Yes.
I hope we have.
Well, maybe I have a comment.
Yes.
Thank you, Ross.
Okay. Well, thanks a lot, Manuela, for a very nice talk. I think, and I really like the idea of the robot not being a super thing, but having to cooperate with humans to achieve the goals. I think this reflects a general trend that we also have not only in service robotics but also now in manufacturing. It is relatively easy to automate a task up to 90-95%. That's typically relatively easy. Sort of the hard stuff is the remaining 5%. Now the trend is, rather than trying to automate everything, to have human-robot cooperation and leave sort of the more difficult aspects to the human being.
That's right. It's a very good point. Indeed, like you say, there could be the case that humans will always have to add things. But what's interesting also about this, like you are saying, is like this concept of asking for help does not limit what researchers can do. The moment that the robot will be able to do more, it will ask for less help. That's okay. So we can pursue this research on better sensors, on better algorithms, on better actuators, but we may believe that it will always have a limit. But who knows? You can still keep doing and incorporating more capabilities. But I insist, and I think that for the audience, I think that the novelty here, in some sense, is that these limitations are not completely predefined. They are proactively found. So, for example, so you have to realize that we face CoBots sometimes stopped in a place that we think it should know where it is, and it would tell us, I don't know where I am, can you tell me? And according to us, there is no reason to be asking, but the fact is that the uncertainty of the world, the lighting of whatever, it may be lost there, or it may need something. So it's proactive. It's the proactive that is surprising, or that is at least the research problem, because it indeed asks for help when the algorithms find that its certainty is below some threshold, or that this action I cannot grab. So that's very good.
Okay.
Thanks, Prof.
Thanks very much. Yeah.
We have a question in Berlin.
Thank you. Yes.
I was wondering if the robots learn from this proactive interaction. For example, it is asked, where is the coffee machine? And the robot doesn't know. And then after completing the task, it updates the map, like saying, here is coffee. And
yes, this is a very good point. I mean, it seems you have read my papers, but it's indeed the case that the robot, every time that it asks for help in terms of knowledge, it does not grow an arm to press the elevator. So the actuator, you don't learn anything. But in terms of knowledge, every time that indeed the robot finds out that coffee is in a kitchen, or that the laboratory is room 7412, it's all learned in the robot. And in fact, currently CoBots have more than, 20,000 facts that he has learned from the interaction with humans, because you have to realize that CoBots have been moving at Carnegie Mellon for more than 300 kilometers or 400 kilometers over the last year and a half, 2 years, 2.5 years. And there is a paper on this on this long-term deployment recent, but it does learn. It does learn knowledge. As I told you, it does not learn to press better the elevator button because it just doesn't have the actuators. But everything that's knowledge-based or sensing-based, it learns description of objects from as soon as I tell you this is a mug, or you here it should be in front of 7412. All the actual things that are not actuation are learned. Okay?
And do they share this information with the other robots? Or?
Very good question. Yes. So actually it's very interesting that, well, they share among themselves. So the three robots, what one learns, all of them know. But we actually have a project now with multiple universities, including Italy, Portugal, China, and the Netherlands, and hopefully also an effort in Spain, in which we are sharing this knowledge, not at the level of the room level, but coffee's in the kitchen, at the level of generalization that is useful for any robot in any place of the world. So we are trying to understand this sharing from a geographically different point of view. But interestingly, I have to tell you something just as a parenthesis. Unlike language, which is not shared among geographically different locations, visual definitions of objects are shared. I mean, we all have tables, we all have chairs, we all have coffee, and, or at least a larger subset is really shared. So all of this knowledge that the robot acquires is very universal, and therefore we are, as we speak, trying to share it among different robots in the world. So if you are interested, send me an email and we'll try to connect with you too. Thank you.
Thank you very much.
Yeah.
So other questions? No, I may have a comment, but I leave for the panel. So.
Sure. Thank you.
Okay.